Okay, let's dive right into this. Have you ever wondered how disease detectives actually use math to uncover public health mysteries? Well, today we're opening up the Epidemiologist Toolkit for this explainer. We're going to explore the exact metrics and mathematical frameworks that public health pros use to track outbreaks, measure disease burden, and ultimately figure out what causes or prevents our most pressing health issues. It's a seriously fascinating journey into the numbers that literally save lives. Here's a quick roadmap of what we're covering. 1. Measuring outbreaks. 2. Tracking flow. 3. Looking forward. 4. Working backwards. And finally, 5. The rare disease assumption. All right, let's hit section 1, measuring outbreaks with attack rate. So we'll start with our first tool, which is deployed when things move fast. We're talking about sudden, localized events, like a foodborne illness hitting a community out of nowhere. This is exactly where we calculate the attack rate. Now, despite its highly aggressive-sounding name, this isn't mathematically a true physical rate because time isn't explicitly factored into the bottom of the fraction. Instead, it's a specific variant of cumulative incidence used for acute, compressed events. It simply calculates the percentage or proportion of people exposed to a specific source who actually end up getting sick. And this brilliantly illustrates how it works in the real world. Imagine a church picnic where dozens of people suddenly come down with acute food poisoning. To find the culprit, epidemiologists survey everyone. Let's look at the folks who ate both the egg salad and the tuna. Out of a total of 75 people who ate that specific combo, that's our denominator, 60 of them became sick. That 60 is our numerator. Divide 60 by 75, multiply by 100, and boom, you get a massive 80% attack rate. That tells investigators exactly where to focus their attention. Moving right along to section 2, tracking flow with incidence and prevalence. Okay, so the attack rate handles those sudden, localized emergencies. But how do we track the long-term burden of a disease across entire cities or countries? To measure morbidity on a larger scale, we use two fundamental concepts: incidence and prevalence. The absolute best way to understand the difference is the classic leaky faucet metaphor. Incidence is the water dripping from the faucet. It measures the flow of entirely new cases developing over a specific time. It tells us the direct risk of catching the disease. Prevalence, on the other hand, is the water already pooled in the sink beneath it. It's a snapshot of all existing cases, both old and new, at a single moment in time. It measures the total burden on the community. Applying this leaky faucet idea to real data makes it crystal clear. Let's take the hypothetical city of Atlantis, population 183,000. Over 6 months, they record 26 new cases of tuberculosis. That is our flow, giving us an incidence rate of about 14.2 new cases per 100,000 people. But if we look at the city's active registry on a single day, there are 264 people currently living with TB. That is our sink, giving us a prevalence rate of roughly 144 per 100,000. So basically, incidence tells you how fast the disease is spreading, right? While prevalence tells you how many hospital beds you might actually need today. Next up, section 3, looking forward with relative risk. We've measured the outbreaks and we've tracked the flow. Now it's time to pivot to the analytical tools epidemiologists use to actually hunt down the causes and the cures of a disease. In the world of measuring disease association, everything orbits around one incredibly important number, and that is 1.0. This is the ultimate null hypothesis anchor. If the mathematical relationship between an exposure, say drinking coffee, and a disease equals exactly 1.0, it means there is absolutely zero association. The incidence in the exposed group is exactly the same as the unexposed group. But what happens when we move away from 1.0? Well, this is how we immediately read our relative risk ratio. If the relative risk, or RR, is greater than 1.0, the exposure is a risk factor. An RR of 1.5 means you have a 50% higher chance of getting sick. But if the RR drops below 1.0, that is actually fantastic news. It means the exposure is a protective factor, meaning it's actively reducing your risk. So the crucial point is how this applies to forward-looking cohort studies. In a cohort study, researchers take healthy people, note their habits, and follow them forward for years to measure exact incidence. Let's consider this data on coffee consumption. Habitual coffee drinkers had a relative risk of 0.81 for cardiovascular mortality and 0.72 for type 2 diabetes. Because these numbers are well below our anchor of 1.0, this forward-looking math proved that drinking coffee actually acts as a protective shield against these chronic conditions. Pretty cool, right? But here's the massive challenge epidemiologists face. Cohort studies take years, sometimes decades, and require thousands of people. What if we're dealing with a rare disease?
Or what if we need an answer right now and simply don't have the time to follow a healthy cohort forward to calculate true incidence?
That brings us to section 4, working backwards with the odds ratio. The solution to our time problem requires flipping our entire perspective. We literally have to work backwards. To do this, we use a case control study design. Notice the contrast here. A cohort study looks forward. You know your whole population at risk, so you can calculate relative risk. But a case control study looks backward. You start with people who are already sick, the cases, and compare them to healthy controls. Because you fix the number of sick and healthy people yourself, you don't actually know the true underlying population at risk. Therefore, you can't calculate incidence, and you can't calculate relative risk. Instead, you calculate an odds ratio. To manage this backward-looking data, epidemiologists use this classic 2x2 contingency matrix. The columns separate the sick cases from the healthy controls. The rows separate who was exposed to a risk factor in the past from who wasn't. We label these cells A, B, C, and D. This elegant little setup is basically the engine that drives analytical epidemiology when total population denominators are completely unknown. Now, what's really interesting here is how the math ingeniously bypasses the need for incidence data. The odds ratio compares the odds of past exposure in the sick group to the odds of past exposure in the healthy group. And conceptually, on our matrix, it forms a perfect cross product. You simply multiply cell A times cell D and divide it by cell B times cell C. It's an incredibly efficient way to establish a strong association without waiting years and years for a cohort study to finish. And finally, section 5, the rare disease assumption. So we have relative risk for looking forward and the odds ratio for looking backward. For decades, these were treated as totally separate mathematical universes. But there is a final, brilliant mathematical concept that links them together, known as the rare disease assumption. Here is how this amazing mathematical alignment works step by step. First, the disease we're studying must have a very low baseline incidence in the population, typically under 5%. Because the disease is rare, the number of sick cases in our study becomes mathematically negligible compared to the massive sea of healthy people. And when that happens, something magical occurs. The backward-looking odds ratio suddenly transforms into a near-perfect estimator of the true forward-looking relative risk. Let's think about the pure mathematical logic here. In our 2x2 table, if the sick people, represented by A, are incredibly rare, then adding them to a huge group of healthy people, B, basically just equals B. The same applies to C and D. When you substitute these approximations back into the complex fractions of the relative risk formula, all the extra denominators literally cancel out, and you are left with exactly the cross-product formula of the odds ratio. This is the ultimate trick in the toolkit. It means that researchers can use the fast, efficient, backward-looking case control method to study a rare disease and confidently report their findings as if they had conducted a massive, forward-looking cohort study. For rare events, backward-looking odds perfectly mirror forward-looking risks. So we've unpacked the attack rates of acute outbreaks, the leaky faucets of incidence and prevalence, and the time-traveling math of relative risks and odds ratios. You now have the exact same toolkit the professionals use to measure disease. The next time you see a sensational health headline claiming a new food doubles your risk of illness, ask yourself, are they tracking a leaky faucet in a cohort, or did they just work backwards through the odds? Armed with this knowledge, you are absolutely ready to be the judge.